Hi, everybody, and welcome to today's problem session for Physics 4C. Today is May 24th, and today we're going to be doing problems from chapter 36. We already started this process, honestly. We did some problems from the past. We did, I believe, let me check the problems that we started with. We did problems 19 and 20. We promised that we will cover at least problems 57, 58, and 61. And I'm going to add to them 62 also because it's extremely important. I was thinking problem 66 and 67, but then I refrained from doing that. Problem 66, actually, we started it already, discussing it when we were doing the in slits, basically, number of slits is being n. And we said you're going to add a cosine or another cosine or another cosine n times, but each cosine, each basically wave, is shifted from the next one by phase shift, phi, let's say, for example. So the first one will be cosine straight out, kx or kr minus omega t. The second one will be cosine kr minus omega t plus phi. The third one will be cosine and so on and so forth until you reach the last one. So each time you're adding a phase shift phi, because basically this is what you're saying. You're saying that you have a source in here, a source in here, a source in here, a source in here. And by the time it reaches a point on the other side, there is a shift, there is a delay. And that delay, because the distribution of this n slits is uniform, so the delay is the same. And the delay is between two adjacent basically sources. So that's why it's cumulative and it's additive until you're toward the end. And I said that summing cosines is not straightforward operation. So what you do in this case, you convert it into complex numbers, because somebody might object, say, okay, you do it cosine, why not sine? Well, do it sine if you like. It's the same thing, cosine and sine. Then in this case, how are we going to handle it if it's a complex numbers? Well, the cosine is just the real part of the exponential of I times the entire phase, including the phase shift. And the sine is just the I mean, basically one operation, 1 over 2I, actually, times the difference of the two exponentials, that's all. So in other words, the real part and the imaginary part of the complex exponential is the same thing. So the problem in there is that once you do the exponential, I'm talking about problem 66 and 67 here, so that you'll keep tab of. So once you're dealing with the exponential, it becomes just basically a geometric sum, okay? And then you add the terms the normal way that you add them, and you will find the sum of n slits. Problem 67 is just an application of that, okay? Application of the same problem 66. So I started thinking that we should do it in class, actually in lecture, and in the past I did it in lecture, actually. But then because it becomes too cumbersome, and we found that in this case doing the phasor method basically with the vector summing and all of that was a little bit faster in giving me the answer. So that's fine, both of them are going to yield the same answer anyway. So whichever is fast. So I'm not going to do problem 66 and 67, but I will leave them for your really general education, that hopefully you guys can go through them and learn how to do these things. Especially if you're a math inclined person, this is a very, very nice practice on how to do these things, okay? But the point in here is that with the phasor method, we were able to find the intensity of the n slits. Okay, problem 57 is the other problem I promised we do. Here is where we stand right now so that everybody knows where we are. Today is Monday. A week from today, there is no class. So, and today we're going to do everything, basically. We did all of the lectures there is. So there is no more really things to do. So today is the last class, in other words. I don't think that we will meet on Wednesday unless you guys want to, unless you request a meeting, then you send me a request and we will meet. And I will send you an invitation for it so that we can meet and so on and so forth. And it does not have to be specifically on the exact class time. It could be before or after. It could be on another day altogether. So you have you can go at your own pace, basically, hopefully prepare for the exam. And I'm going to talk about the exam before the end of today's session. Okay, so let me share with you the screen. Share. And hopefully by now you have a piece of paper handy and your pen or pencil is ready so that to follow. So the next problems I'm going to do are problems 57, 58, 61, and I'm going to add to them 62. So those are the 4 problems, in addition to the 1920 that we did last time. So today is 5/24. Okay. The problem 57 is kind of short problem, a sweet problem, but it requires some work. So it says that diffraction grating has 650 slits per millimeter. So the number of slits is 650 slits per millimeter. In other words, if I take a millimeter of this one, this is a whole millimeter, I have 650 of them in here. So the spacing between each and every one of them, D, is going to be basically 1 millimeter divided by 650. So that is going to be D. So from here, we have the value of D. So let me put the value of D. Value is D is equal to 1 over 650, but 10 millimeters. So it's going to be 0.015. So it's going to be 1.53 times 10 to the negative 6 meters or micrometer. So we need the D, okay? 1.53 times, yeah, we need the D. So this is the distance between the 2 slits. And then it says in here, what is the highest order that contains the entire visible spectrum, the wavelength of the spectrum, visible spectrum. So the visible spectrum they gave you in here for the lambda for the violet, which is the shortest wavelength that is given to you in this case, is 380 nanometers. And the lambda for the red, which is the longest wavelength of the 2, is 750 nanometers. Okay, so we have the 2 wavelengths, and we want to find the highest order. Let me tell you how you find the highest order in this case. We know that we will have actually a wavelength in this case whenever this relationship is true. D sine theta is equal to m lambda. Okay. Well, I have 2 lambdas. We have lambda for the red and lambda for the violet. So I really have to be careful in here which one I mean and which one I'm talking about. M cannot, sine theta cannot be greater than 1 in magnitude, of course. So I'm taking m positive. So that means that d sine theta, which is m lambda over d, cannot be greater than 1, because that's exactly what sine theta is. So in this case, m cannot be greater than or equal to d over lambda. So this is the maximum order I'm going to have for each and every one of them. I have the value of d, because remember, I have 650 slits per millimeter. So over 1 millimeter, I have, the distance between each 2 is 1 millimeter divided by 650. So that's how much they are separated from. And now it's a matter of just finding the values in here that correspond to this expression. M for red. So let's start with red. M must be less than or equal to, it's an integer, by the way, m. So it's an integer. It's not a real number. So it's d over lambda. And how much is d? It's 1.53 times 10 to the negative 6 meters. That's what this number means. 1.53 times 10 to the negative 6 divided by the wavelength for the red is 750 nanometers, which is 750 times 10 to the negative 9 meters. So obviously, if I put this in a calculator, 10 to the negative 6 and 10 to the negative 9, I will be down to 10 to the negative 3. So this number is 1.53 times 1,000 divided by 750. Or, if you wish, 1,530 divided by 750. So m is an integer that must be less than this number. And how much is that? Did I put it right in here? M lambda, yeah, that's m lambda is equal over d.
So M is less than or equal to, yeah, that's correct. So should have no problem. So now it's this number, let me write it down, 1,538 actually. I rounded it down, so it should be 38, divided by 750, as if this makes a difference. It's 2.0 something. Okay, so M can be 1 or 2. Cannot be more than that. Cannot be 3. So that's for the red. For the violet, M must be less than or equal to the lambda for the violet is 380. So it's going to be 380, the same algebra basically, times 1.53 times 10 to the power 3. So I already did the simplifications in here. So it's 1,530 divided by 380. So this should be, according to my calculator, oops, I deleted the whole thing. I don't mean to do that. Hopefully you guys are doing this math in here. 380. Okay, 1,538 divided by 380. Save time. So this is 4 point something. So that means M at most is equal to, M is equal to, for this one, M is equal to 1, 2, 3, and 4. Okay, these are all valid angles. However, you have a problem in here. Since you want the entire spectrum, you cannot have anything more than this. Okay, more than 2. So for the entire spectrum, those are the angles that you're going to have. You will have the red actually satisfying this condition now, since M is equal to 2. So I'm going to find sine of theta 2 now. Sine of theta 2 is equal to 2 times lambda divided by d. And that means that theta 2 is equal to basically the inverse of this operation, which is 2 lambda over d. And if I plug in the numbers in here, I have 2 times lambda for the red. I have, let me write it down, arc sine of, open parentheses, of 2 times lambda for the red is 750 nanometer divided by 1,538, basically, when you do the conversions and everything. And it's saying me that this angle is 77 degrees. Let me make sure that I'm using the degrees in here. So this angle is 77 degrees. That is the second order, okay? The first order is some other value in here, which is probably half of this angle or something like that, okay? You need to do the calculation for that. So if I plug in n equals to 1, so I have 29 degrees. So in other words, the red will be at 29 degrees and 77 degrees. Okay, both of them will have red in it. How about the violet for the same order? For the violet, I will have sine of theta 2, which is a different angle, which is again 2 lambda over d, which means that theta 2 in this case will be the inverse of 2 lambda over d, which is, now I have to put the value of this lambda, not the other one. So I'm going to put it in here. I put the 2 back. And the value of the angle is equal to 380, 380. Okay, so this angle is 29 degrees. 29.6 degrees, so it's going to be 30 degrees. Okay. Whereas the first angle is 14 degrees. So violet will be between, the first one will be 14 degrees and the second one will be 30 degrees. So this is how the spectrum look like. So I will find in here, so this is the central. I will move in here, I'll find first of all the violet, the first violet. Then I move in here, I find, what is it, 29 degrees, that's the first red. And in here I will find the first violet next to it. And next to it, I will find in here, very far away, the second red, second violet, and the second red. And if I keep on looking, I can actually have the 3 and 4 actually too, because this equation can be satisfied for 3. So if I plug in here 3, I'm using the calculator, so hopefully you guys can do the same thing. So if I plug in 3 for the violet, I will have 47 degrees. So somewhere in here, there is another violet in here. That's violet 3. And actually, I have another one also. This is not all of it, so I can have around probably 77 degrees, maybe slightly less than 77 degrees. Let me put 4 in here. No, actually more. 81 degrees is the other one. The other, so this is 47 degrees. This is the third violet. And the fourth violet, if I'm asked for it, is going to be at 81 degrees. Okay, this is the fourth one. But I'm asked for the entire spectrum. So the entire spectrum will be here. The second one. Make sense? Good. Okay, let me put guys in the chat in here. Okay, very good. So let's move on to problem 58. Problem 58 is very verbose. This was 57, by the way. So far, we did this problems in here. 57, 58, and then we're going to still have 2 more. Excuse me. Okay, it says quasars, an abbreviation for quasi-stellar radio sources, are distant objects that look like stars through a telescope, but that emit far more electromagnetic radiation than entire normal galaxy of stars. An example is a bright object below to the left. So they give you a picture of a quasar. So basically what a quasar is are galaxies with super active black holes basically in their center that are feeding usually, and in doing so, of course, the matter that is falling in, for the conservation of momentum, some of it is ejected out, and those ones that is ejected out comes out with speeds that are very, very high speeds. As a matter of fact, very close from the speed of light. Usually there is tremendous amount of the magnetic field that is associated with it, and that causes basically the particles to escape into tremendous velocities. Anyway, the other elongated object in this image, so basically you're trying to find a picture of a quasar. You would want to take a high resolution picture of a quasar. Because very far away, very faint, so you need to have a huge, basically, telescope to look at it. So that's basically the whole problem. In order to collect as much light as possible from a very small area, because it's very far away. So the other elongated object in this image are normal galaxies. So the picture actually shows quite a few galaxies next to it. There are at least 1, maybe 2 or 3. Okay. This is a picture taken, basically. This is a real picture of a quasar. I mean, of course, it's not the high resolution because you take an entire galaxy that is several times probably the size of our own galaxy, Milky Way, and you put it in a picture this size. Of course, it's not going to be. Anyway, so you're not going to see a lot of details. You're not going to see the black hole or the stars in it or anything like that, because this spans several light years, actually, if you think about it. The leading model for the structure of a quasar is a galaxy with a supermassive black hole at its center. In this model, the radiation is emitted by interstellar gas and dust within the galaxy as this material falls toward the black hole. The radiation is thought to emanate from a region just a few light years in diameter. So the black hole is actually supermassive. I mean, it's much, much bigger than the solar system itself. Imagine what created it. But the point being in here is that there is a huge region that you would want to take pictures of it, okay?
the diffuse glow surrounding the bright picture that is in the picture is actually not the black hole, but that of the is the host galaxy, basically, all of the other stars. The light is basically going through them. Quasars are very, very dangerous, basically, galaxies. Now, models basically suggest that there is no way that in a galaxy of such a high intensity, basically, radiation could have harbor life. I mean, if our own galaxy goes quasar, there is nothing can survive it, because the entire galaxy will glow, basically, with extreme high radiation and intensity. So it's really ridiculous. So anyway, to investigate this model of quasars and to study other exotic astronomical objects, the Russian Space Agency has placed a radio telescope in a large orbit around the Earth. When this telescope is 77,000 kilometers, that's basically the radius of the aperture. So, okay, from Earth, from the ground-based telescopes of the VLBA. VLBA stands for Very Large Base Astronomy or something like that. No, a Very Large Base Array. That means that you have an array of telescopes. You have a telescope on the Earth and a telescope on the in orbit, and probably another telescope somewhere else on Earth. And what you do in this case, you collect the light from them and you synchronize them so that they all will give you a basically different side of the same picture, as if you have one huge giant telescope. That's the whole purpose of this one in here, because sometimes the objects are too far and too faint to be, no matter how big your telescope is, it's not going to collect any light. So what you do in this case, you make an array of them and you make them act in sync so that they all point to the same object, and now they all become like a huge, basically, telescope. So that's what this thing is. So basically, think of this whole system now as if you have one single telescope that has a diameter or has a radius of 77,000 kilometers. That is basically how you can think of this problem. So the resolution is that of a single radio telescope, 77,000 kilometers in diameter. Okay. What is, so this is the diameter, not the distance, okay? What is, yeah, because one telescope, one here, and another telescope, one here, so the distance side to side is really the entire diameter. Okay, that makes sense. So the question is, what is the size of the smallest detail that this arrangement can resolve in quasar 36405? The quasar 36405, they give you the distance, and the distance is 7.2 times 10 to the power 8 light years. In other words, 720 million light years away from us. So this is very, very far. Of course, it's not the furthest object. Things are in the billions of years and in billions of light years away from us. So, using radio waves as at the frequency of 1,665 megahertz. Hence, use Rayleigh criterion. You give your answer. So here is the deal. So we're going to go into, we're still sharing. So here is the deal. So what you have in this case, you have a telescope with an opening D. So this is the diameter D, which is 77,000 kilometers. Okay. You have the wavelength that satisfies the equation. First of all, the dispersion law, omega equal to kV. I don't remember it in this. It's the distance omega kV. So the k in this case, which is 2 pi over lambda, is equal to omega over k. Okay, omega over v. Sorry, omega is 2 pi f divided by c for light. So light, lambda will be c over f, c times f. No, c over f. Okay. Basically solve this equation now for lambda. Move lambda to the other side. So this is how much, this is the wavelength basically of the light. Because they gave us the frequency, they didn't give us the, so the frequency is 1,665 megahertz.
So in this case, the wavelength is 3 times 10 to the power 8. That's the speed of light, meter per second, divided by a 1,665 times 10 to the power 6. The wavelength in this is 1/second. The frequency is hertz. So it's going to be 300 over 1,665. 1,665 to C6 is only 3 of them. Meters. Okay. So let me get this number because we will need this number for our calculation. We will need lambda. 300 divided by 1,665. And the answer is 0.180 repeating. So this is 180 millimeter repeating. Okay. Or if you wish, 18 centimeters. 18.0 centimeters. Okay. So that is the wavelength. Okay. Which is a typical wavelength. So this is a radio range. So this is a radio wave. But that's not the question, of course. They want what is the size of the smallest detail? So the smallest detail. Here is the object in here. Let's assume this is how big the object is. So this is the actual quasar. This is the distance to it from Earth. So this is basically the object. I can find the sine of the angle or the tangent of the angle using, because the angle is very small in this case. So the sine of theta or tangent of theta, if you wish, they are the same angle, which is theta in radians, must be equal to the size of the object, which I'm going to call O, or the resolution in this case. Resolution. In other words, the smallest distance, let's call it, let's call it D. No, I don't want to call it D because we already have, let's call it resolution, leave it as it. Divided by R. I'm sorry, that's because I didn't do this problem. So I'm I did not decide on the signs in here. So we have basically, we want the R, but we know also another thing in here, that in order to have a resolution, this is basically the sharpness of the image. The first dark, according to the Rayleigh scattering, is given by, if you remember, what is it? D sine theta is equal to 1.22 lambda. Okay, and we know that I'm sorry, big D. We know that D, the diameter in this case. So we are given the diameter, and we have sine theta from this expression, and we have lambda. So the only thing in here that we are missing is this resolution. We know the distance, how far the object is in light years. So we have everything. So R is given to be equal to how far is it? 720 light years, 720 million light years. Okay, that's the distance actually in light years. Now we have everything. So all we need is the resolution, which is R times sine theta, and sine theta is equal to 1.22 lambda over D. So we have everything in here. So the resolution in this case is going to be R times sine theta, and sine theta is equal to 1.22 times lambda over D. So we have everything. So we have R, which is 77,000 kilometers. Oh, not 77. What am I talking? That's D, actually. I'm sorry. We have R, which is equal to 720 million light years. Okay, times lambda. Lambda times 1.22 first, times lambda, and lambda we just found it to be. I have to convert it to kilometers, or I have to convert kilometers to meters. So I'm going to leave it with meters. The way it was with meters, 300 over 1,665. So this is in meters now. The distance D, this is lambda. The distance D is 77,000 kilometers, or 77 times 10 to the power 6 meters. So this guy is in meter, this guy is in meter. The answer is going to be automatically in light years. Cancel the mega with the mega in here, because both of them are 10 to the power 6. So we'll be left with the following numbers, and the answer is going to be in light years, by the way. 720 times 1.22 times 300 divided by 1,665, and the answer is going to be in light years. So this is how good is this telescope is, how it's going to resolve these things. So let me do the math in here on this calculator. So I have 720 times 1.22 times 300 divided by 1,665, and the answer is 92 light years. So the resolution of this device is 92 light years. In other words, if the quasar is bigger than this size, is 92 light years or bigger, then this will give you an image that is good enough for it. But if it is smaller, it cannot resolve objects less than this. They're too small for it to be found. And 92 light years is a huge distance. Just to give you an idea, the distance between the sun, which is our star, and our next door neighbor is 4.2 light years. So this will not resolve the two stars. It thinks only it's one star, actually. Okay, do you see that? As a matter of fact, you can go further than that. You can take a Ryger, for example, or a Sirius, for example, which is about what, 8 light years from here. It doesn't matter. They are too small, a lot smaller. As a matter of fact, take the entire galaxy that we live in, edge to edge, from this star on one edge and the other star to the other edge. It's about 100,000 light years. So this is not even one. No, I'm sorry, 100,000, that's going to be resolved. I'm sorry, I thought it's in different units. I thought I was using different units. Okay. Sorry about that, okay? So the entire galaxy will be for sure resolved because it's very big. But I'm trying to come up with numbers in here. For example, how far is Ceres? Is it 25 light years? No, Ceres is only. I'm trying to find a star that is within this range, okay? Yeah, it's 8.6, so it's very close in here. Vega is 25 light years from here. Vega. I think Vega is only 25 light years. I don't think it's too. Yeah, 25.05. So which star is 100 light years from here? Or 92 at least light years from here. I know Betelgeuse is about 500 light years from here, so it's very far. Betelgeuse will definitely be resolved. Okay, because it's, I mean, the sun and the Betelgeuse, or at least a group of the stars, including Vega, which is a very big star, and Betelgeuse, they will be resolved because they are actually more than 92. So let's see here, stars within 100 light years. Oh man, the question is already there. This is our neighbors, I mean, things that you can see with such a telescope, okay? Man, this Wikipedia gave me stars only up to 16. Never mind the question, okay? Hopefully you get, no, there are more data in here. Never mind. Never mind. Please find any star that is within this range because I Googled it and I could not find anything that, I know some stars that are more and some stars that are less. But, I mean, it gave me stars that are like 16 light years. What am I going to do with it? I know Vega is further than that. Okay, here are the stars. Here are the stars. Algol is within 92.8. That's going to be within reach, but that's not the famous star. Let me find something that is within nothing in here that they can think of. Anyway, They're probably not known anyway. So that's the point in here for this problem. So basically what you're supposed to do in this case is basically use Rayleigh scattering from, oh man, why is that? Use Rayleigh scattering, which is a condition to find the first minimum, which is at 1.22 times lambda over d to find sine theta, basically. That is the sine theta. And use the distance, which is given to you, r. And from here, you can find how big the object need to be, because you know tangent theta is equal to that object size divided by r. And that's basically how, in a nutshell, how this problem is set up. So the next problem, let me share with you so that you can see where I am at. Where is the screen? So the next problem that I promised we should do is problem 61, and then we're going to do problem 62. So both of these problems are, no, actually not both of them. One of them is data problem. No, actually both of them, which means they are extremely good candidates for exams, okay, or versions of them, okay? So both of them are data problems. So you need to pay attention to this kind of problems. So let me look at problem 61. Problem 61 really cannot be done that way. It has to be done. Can I get that camera? Because I want you, if you don't have your book, you really have to look at the picture. So hopefully you have the picture with you for the problem 61, because you need the picture. And that is sometimes you'll be given a picture and you're supposed to analyze it. So let me read the problem first before I put the book under the camera. It says, while researching the use of laser pointers, you conduct difference. So this is 61. You conduct a diffraction experiment with two thin parallel slits. The result is in the pattern of closely spaced bright and dark fringes shown in the picture. So they gave you the picture. Only the central portion of the pattern is shown. You measure the bright spots are equally spaced by a distance of 1.53 millimeters. So the distance between them, this bright and this bright, this is, I'm going to call it y, is equal to, so basically, let me draw the picture here, how it looks like. So I counted them already. I have 13, so let me accommodate for 13, because this is not going to accommodate for 13. So I have one bright, followed by another bright, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then there is nothing in here. And then after that comes 2. Same thing, there is nothing in here. And then after that comes 2. This is the picture that they drew for you, basically. This distance and this distance is given to be 1.53 millimeter. This is on the screen. Okay. If you start counting from the center, so if these are 13, 1, 2, 3, 4, 5, 6, 7, this is the middle. This is the center. And there are 6. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. The 7th is a cancellation. So what I have in here, I have slits that are separated by distance d, and they have width of a each. So where d sine theta is equal to m lambda, I have constructive interference. And I have it for m equals to 0, of course, and for m equals to plus or negative 1, for m equals to plus or negative 2, for m equals to plus or negative 3, for m equals to plus or negative 4, for s equal to plus or negative 5, for m equals to plus or negative 6. And then for m, where it's supposed to be 7, there I have another equation that says a sine theta is equal to m prime lambda. This point in here corresponds to m prime, which is equal to 1. Because there is a cancellation in here, because of that, that is 0 anyway. So m equals to m prime equals to 7. I mean, m prime equals to 1 and m prime equals to 7. That is the same point in here. Then this becomes m equals to 9, actually. I'm sorry, 8, because we skipped 7, 8, 9, and so on and so forth. Okay. So that's how the spectrum look like. Okay, let me show you. Let me put the camera in here and let me bring this one closer because it's much easier to probably do it that way. Book. Hopefully you guys have the book too. I'm not relying on my cameras in here. Let me stop sharing and let me switch cameras. It's this picture in here. Okay. So what you have in here, you have them again, 1, 2, 3, 4, 5, 6, 7. That's the center. 8, 9, 10, 11, 12, 13. So you have 3 on each side, 6 on each side for a total of 12. And you have the central one. I'm the one who put the markings in here, so it was not there. So if you look at these things with the marking, that's what you see. And then that means that I am counting. It doesn't matter positive or negative in here. So if I call this one negative, this one is positive. So I have 1, 2, 3, 4, 5, 6. And m equals to 7 corresponds to m prime equals to 1. That is where they cancel. And then I have, of course, comes after 6 is m after 7 is 8, 9. Okay, same thing on the other side, -8 and -9 and -7 where the cancellation happens too. So this is a spectrum that you're supposed to analyze, basically. And hopefully you guys will develop enough techniques to do that. Let me switch cameras. Okay, so that is the thing that I drew in the picture. So let me move this camera out of the way and let me share again OneNote. Okay, so we have that. The light source was a helium neon laser producing a wavelength of 632.8 nanometer. So we know lambda, 638.2 nanometer. We're given lambda. How far apart are the two slits? In other words, D. We know that D sine theta is equal to m lambda. For m equals to 1, we know the distance here. Did they tell us how far is it? It's 2.5 meters away. So this one is 2.5 away from the source, 2.5 meters away. So in other words, we're given this distance, and we know for small values of m, for the small angles, d sine theta, in this case, is equal to lambda, but also sine theta is roughly equal to tangent theta, and tangent theta is equal to the ratio of this distance, which I'm going to call it y, divided by this whole r. So we have theta from this equation, and we have lambda given, and we have m equals to 1. So from here we can find d. So d equals to lambda, and lambda is 638.2 nanometers, divided by sine theta, and sine theta is basically y over r. And y over r is, so it's 638.2 nanometers divided by y, and y is 1.53 times 10 to the power, what is it, millimeter? Yeah, millimeter. So it's 10 to the negative 3. And the distance is just 2.5 meters. So this units cancel because I converted this one to meters. 1.53 millimeters and the 2.5. So the actual unit for D is going to be in nanometers. So what we have in here, we have 2.5 times 638.2 divided by 1.53 times 10 to the negative 3, and it's in nanometers, which is 10 to the negative 9. Obviously, the negative 9 and the negative 3 cancel, and I will be left with a negative 6. And the D now can be managed, okay? So let me plug in things in the calculator. So I have 2.5 times 638.2 divided by 1.53, and it is 1042 micrometer, but we don't really need it in micrometer. We can use a millimeter. So we're going to write it as 1.042 10 to the negative 3 after that, which is millimeter. Please handle your units correctly, okay? And conversions and all of that. You really have to be focusing here in order to get these things right. So we found D. Since we were given this distance and we took the first one, if I want the second one, I have to multiply that by 2. But I have to be careful with large angles because things with large angles don't work out so well for you because of this approximation. So sine theta is not tangent of theta. In other words, you have to find tangent theta, and then you find theta, and then you find its sine, and then you plug into this expression. So the only reason why I did it this way is because I know sine theta is equal to, I mean, if you don't trust me, just do this. What is 1.53 times 10 to the negative 3 divided by 2.5? Obviously, this number is very, very small, okay? And this is actually theta in radians. So if you do that, try sine of this angle in radians and tangent of this angle in radians, and they will be identical, provided this is in radians. Very important. And I've had students in the past where they get confused. They forgot to convert things, and they ended up with some wrong answers because of the fact that this is equal to theta only and only if theta is in radians, not any other unit, not in grads or degrees or anything like that. Okay, so we have D. And the next question is, how wide is each one? Basically A. So now we have D. I need to find this angle. Obviously, this angle is not going to be a small angle. This one or this one, it's the same thing. So this is the first theta that corresponds to m prime equals to 1. So we know for m prime equals to 1, A sine theta is equal to lambda. We have, so this is the dark, okay? The first dark. We know lambda. We don't know A, and we need to find this sine theta dark. Well, sine theta dark corresponds to a bright spot in terms of the other ones. This is of the order of 7. The only reason why we don't see it is because it's canceled by the single slit, that's all. So we know that D sine theta dark is equal to 7 times lambda over 7 times lambda. That's it, okay? So in other words, I know what sine theta dark is 7 lambda over D. And from here, we can find what A is. A is going to be lambda over a sine of the theta dark, and we were able to find it using the the double slit. So it's lambda divided by 7 times lambda over D, cancel the lambda and the lambda, and as expected, it's D over 7. In other words, you really don't need to do much calculations because you know the 7th bright fringe from the double slit is the first dark fringe from the single slit. So there is a 7-to-1 ratio in this case between the separation and the width. 7-to-1, because the 7th bright one is the first cancellation here. So there is actually a simple ratio in here. So since we found D to be this number, all I have to do is divide it by 7 to find how big A is. So A should be 1.042 divided by 7, and the answer is going to be in millimeters. So it's not 2, it's 3. I'm sorry. I rounded down. It should really be rounded up because 428. Hopefully, you guys are not relying on my numbers. You're doing your things on your own and finding all of these mistakes, okay? So now I have to use a calculator again. 1.043 divided by 7, and that is 0.4149 millimeter, okay? Or 14.9 or 149 actually micrometers. Obviously, it's going to be smaller. It should be smaller than the separation between the two. Does this problem make sense to you guys? Yes, no, maybe. Okay, very good. Very good. So we're going to go to the last problem that I promised we should cover and talk about the problem that I did not mention here in the list, but hopefully you guys can see also. So the problem is 62 now. 62 is a bunch of data, so probably I should get Excel going. I'm going to move it to the other side. The screen. So let's get to the problem first. Your physics study partner tells you that the width of the central bright and band in a single slit diffraction pattern is inversely proportional to the width of the slit. So the central band, remember, for the single slit, like the previous picture I was sharing with you guys in here. Where is it? Problem 5061. Here, this is the central band for the single slit. What he's saying is, if you make A smaller, it grows linearly with it. Okay, it grows linearly, inversely. I'm sorry, with A. So if you make A smaller, this grows inversely with one. Linearly with 1 over A. Basically, that's what he's saying. Okay. Your physics study partner tells you that the width of the central bright band in a single slit diffraction pattern, because this entire thing will be a single slit, okay, is inversely proportional to the width of it. This means that the width of the central band increases when the width of the slit decreases. So if you make A smaller, this will become bigger. And that's true. There is no problem with that. However, the claim seems counterintuitive to you, so you make measurements to test it. You shine monochromatic laser beam with wavelength lambda onto a narrow slit with width A and measure the width W of the central slit. So you basically, what you do in this case, you change A, and as A changes, you're going to measure basically how wide they are, the width of this thing in here. Okay. In the diffraction pattern that is produced on a 1.5 meter radius, distance. So R is equal to 1.5. So R is fixed. R, how far is the screen from the slit, is 1.5 meter, meter and a half, 150 centimeters. Okay. From the slit, by width, you mean the distance from the center, from the screen between the two minima. So this is the width that we're talking about. This minimum and this minimum. This dark and this dark. So that's the width we're talking about, so W. Okay. Excuse me. I think I need to get some coffee. Your measurements are in a table, so they give you a table where A is in micrometers. Very important to pay attention to the units. And W is in meters. The width is in meters. Okay. It varies almost 3 meters all the way to 10 centimeters. If W is inversely proportional to A, that's the question A, then the product AW is constant independent of A. For data in the table, graph AW versus A. Explain why AW is not constant for small values of A. Let me graph this thing. So let me stop sharing. So whenever you're doing an Excel problem, an exam or otherwise, try to put it how Excel likes it. I mean, in the problem, they give you things in the horizontal direction, because if they did it in the vertical direction, they are out of space, and the book will be probably
maybe a few more dozens, basically larger than what it is already. So they put the lines horizontal. When you do them on Excel, put them on vertical lines so that you're ready to graph stuff. So again, so what do we have now? We have A, and make sure that it's in micrometer. And then we have W, and W is in meters, okay? So the first values are 0.78, 2.68. I'm going to go down through all of the other 0.91, 104. Make sure you don't miss any points in here when you're doing these things in here, because you could end up with an extra or short of values in it. And make sure you enter them correctly, otherwise you get more errors. Okay, 5.2, 7.8, 10.4, and 15.6, 15.6. Hopefully I did not enter any number wrong. So the first one is 1.68. I mean 2. Oh man, it's not 1.68, 2.68. 2.68. And then 2.09. This is a type of questions you might have at least one or two of in an online exam, okay? And each and every one of you will have his or her own different questions. So 1.73, 0.89, 0.51, 0.3, 0.2, 0.15, and 0.1. So this is the data for AW. They said multiply A by W and give us the graph. So this is AW. And it is exactly what it is. So I'm going to say equals to this cell times this cell. Oops, no, times this cell. Good. And that is the product of this too. So I'm going to copy this value and put it in here. Here is what they're saying. It stabilizes, I would say, from 6. It becomes more or less constant. After that, before that, it's not really constant. So you cannot say. So let me graph this AW as a function of A. So this is my y-axis, I mean x-axis, and this will be my. I am holding the control key to select both of the cells so that I don't select the middle one, okay? Or I can put them next to one another and select them, it's fine. Oh man, I didn't mean to do that. Okay, let me move this out of the way completely. Go back to Excel, go to Insert, and we want a chart, and we want it with data, except, oh man, we are not supposed to do that. We're supposed to, are we supposed to do that? Yeah. That's fine. Sorry about that, okay? So let me plot it again. A is getting bigger. As A is getting bigger, the width is getting smaller. That's how it's supposed to be. Okay. So again, why do I have it backward? No. Give me the wrong thing in here. Let me delete this thing in here. That's not the graph I want to have. Okay. So let me copy this since it did not work out for me in here correctly, and let me paste the numbers. Let me copy this and paste it in here. And let me do it normally in here. Insert. Again, chart.
This is better now, okay? This is better now. It's supposed to be constant at the end and changing in the beginning. So, except I don't like the scale. Can I change the scale a little? Giving me the automatic. I mean, it's the point is there. If you guys can clearly see it, it's there, okay? But I want to see, can I do a logarithmic? No, that's even worse. Okay. Since the maximum value in here and the y-axis is 2. So I'm going to do 2.1. Okay, how's that? And since the minimum value is 1.5, so I'm going to put it 1. That's going to fix the problem. That's going to give me a better analysis. That is my argument in here. So I'm going to put this one 1.5 actually, and this one 2.5. How is that? Because we know how this thing is changing, and even 2.5 is not good. Let's put it at 2.2. That's good enough. Okay. She clearly see from this graph in here. When you're doing graphs like this, well, let me move it to its own chart. Move to, where's the move? Okay, so when you're doing things on Excel and there is a behavior you're looking for, you can actually look for it by rescaling your axis. And I always make an argument for when you're doing your labs to pay attention to this detail. It helps you basically analyze your data better. You know AW is constant in this region from point 1, 2, 3, 4. So the last 4 points, it's more or less constant. Initially, it's not constant. It's clearly not constant, okay? So in other words, if I go back to my data, the last 4 points, 1, 2, 3, 4, they are all constants, and the product is actually constant 1.56 micrometer meter. Okay, the product is constant, and from the first values, it's not. It's changing actually, and it starts from 2 down to 1.6, and then after that stabilizes. So for large values in here, it looks like it's good. For large values of A, it seems like it's working, but for small values, it's not correct, okay? So let's see why that is, because they tell you, the question was, for the data shown in the graph, explain why AW is not constant for small values of A. So for small values of A, what's going on? So let me stop sharing. Let me share with you the analysis in here. And let me move this thing out of the way. So basically for small values of A, what we have in this case is, we have, first of all, we know that in this case, A sine theta is equal to lambda. This is the first one. This is for m equals to 1. Sometimes I use m, sometimes I use m prime just to make a distinction when I have both the single slit and the double slit. But if I only focus on one of them, I use just a single letter m. Like in the previous problem, I had to use both m and m prime because I have both of them. So m in that situation was referring to the double slit, and m prime was referring to the single slit. In this case, I'm using only one of them because I'm varying the width A of a single slit. So in this case, it doesn't matter. It doesn't make sense to call it m prime since we only have one of it, so it's m. So in this case, this is the first place. So in this case, here is the thing. This is the angle theta that we're talking about, and this is the same angle theta that we're talking about. Yeah. So if A is small, clearly sine theta is inversely proportional to A. So if A is small, the angle becomes big. And then we cannot use the simple relationship theta is equal to lambda over A only for large A. For small a, sine theta is not equal to theta. Okay. Furthermore, sine theta is equal to roughly tangent of theta. For small theta also, only. Okay. So in this case, the tangent theta, and tangent theta is this distance, which is whatever, we're going to call it y, divided by r. And twice distance is the width we're talking about. Twice 2w is the 2y is w. So in this case, for large values of a, sine theta becomes very small because lambda over a is small. Then sine theta becomes small and roughly equals to theta, which is roughly equals to tangent theta, which is then gives me this relationship that the w, which is 2y, and y is equal to r tangent theta. So basically, in this case, w will be equal to 2r times tangent of theta. And tangent of theta in that case will be simply 2r times sine of theta. This is for large a, which is in this case 2r times lambda over a. In that case, a times lambda will be just 2r times w times lambda. For large lambda, so it's not going to change anymore. So if change from an a that is this size, for example, I'm looking at the data, 5.2 micrometer to 7.8 micrometer to 10.4 micrometer to even 15.6 micrometer, the number a times w stays the same, and it's just 2r times the wavelength. And r is the distance from the slit to the screen, and lambda is the wavelength, which is not changing. It's the same laser beam. So since that doesn't change, this value does not change. It stays the same. But for very small values of a, we have a disaster because, yes, lambda over a is equal to sine theta, but sine theta is not equal to tangent theta. So I cannot use this approximation. This step is a no-no. So in this case, I cannot say w is proportional, inversely proportional to a. That's why in the graph that we drew, let me stop sharing the screen and go back to the graph so that you guys see what I'm talking about in here. That's why the graph on Excel, for large values of a, it does not change. A times w is constant, and it's equal to 2r times lambda, actually. But for small values of a, it's no longer constant. It's actually, because sine theta and tangent theta are not the same, they're different. So that is the problem that we ran into. That is the description of this graph. So that is how this data that we collected is behaving. So let me stop sharing and share with you the OneNote. So we have that. Question A. Question B. Use your graph in part A to calculate the value of lambda from the laser beam. Okay, we have found that 2r of lambda is equal to AW, and AW, if you remember, is 1.56 micrometer meter. Those are the units we used, okay? And 1.56 times 10 to the negative 6, that's what the micro means, meter squared. And we know R they told us is specifically equal to 1.5 meters times 2 times lambda. From here, we can find, first of all, one of the meters cancels the other meter, and we can find what the value of lambda is. So the value of lambda is going to be equal to 1.56 times 10 to the negative 6 divided by 2 times 1.5, which is 3. So if I do the calculation correct, and if I didn't make any mistake in this thing, let me go to Excel. Excel is already in here, so why don't I use Excel to find the... Okay, so this is equals to
1.56 divided by 3,
which is 0.52 times 10 to the negative 6 meters. And that, if you divide by 1,000 and you multiply by 1,000, it's going to be 520 nanometers, which puts it right in the green region. So this is a green laser beam. Okay. So that is basically the answer to the question.
What is lambda? Okay. What is the angular position of the first minimum in the diffraction pattern for A equals to 0.78 and A equal to 15.6? So we want the first, what is the angular position? What do we want theta?
For both A's. So we have two A's. We have an A. So here is where it goes wrong, okay? So do not rely on the numbers that you have from the table. You have to use the data that you have in here. So you have lambda now, and you have A sine theta is equal to lambda, basically. Which means that sine theta is equal to lambda over A. Obviously, for the first A, sine theta is equal to lambda, and lambda we found at 520 times 10 to the negative 9, divided by A, and A we found it to be, how much is it?
No, A is given actually. A, they said to use 0.78 micrometers
or 780 nanometers. Okay, so that the cancellations. Basically, sine theta or theta is going to be arc sine of 52 over 78. Okay, I don't like Excel for this one because Excel will give me the angle in radians. I have to convert it, so I don't want to do that since this calculator give me in degrees. I want to find arc sine of 52 over 78. And this answer is 41.8 degrees or 42 degrees. You see here? This is a small value of A, and the angle is not small. 42 degrees is not small. If we do it for the second one, I bet we're going to find it small because the second one is A equal to 15.6. 15.6, it should be small. So for the other one, sine of theta again is equal to 520 nanometers divided by 15.6 micrometer. So again, this is 10 to the negative 9. This is 10 to the negative 6. And then I'm left with 10 to the negative 3. It's clearly the number is very small now. So theta is going to be arc sine of 520 times 10 to the negative 3 over 15.6. So let me plug in the numbers in here in the calculator. And hopefully you're doing the same thing. You're not relying on my numbers in here. So I have 520 times 10 to the negative 3, which I could have done quickly, but it's fine, divided by 15.6. And the angle in degrees, it's 1.91 degrees, okay? Theta is almost 2 degrees. As it should be. For large values of A, the angle is small. That means it's a high resolution. That means this is independent of the angle. That means sine theta is equal to theta, is equal to tangent theta. But theta is in radians in there, okay? Okay, hopefully this problem is clear enough for you guys. Okay, so basically, this exam is going to cover chapters 33, chapters 34. Chapter 33 basically has two equations, namely theta 1 is equal to theta 2. The angle of incidence is equal to the angle of reflection. And the other equation is that n
1 times sine theta 1 is equal to n2 sine theta 2, where 1 in here reflects to one medium and 2 reflects to a different medium. So you have a refracted angle in this case. The next chapter, the image formation, is an important chapter. So I know we did a lot of problems with them. So hopefully you guys have seen, go through them. And if you have any questions, the exam is not this week. The exam is actually next Wednesday, not this Wednesday, next Wednesday. You have about 10 days. So please go through all of the examples that we did, make sure you understand them, make sure you have no questions, no ambiguity about them and things like that. And then, first of all, how about chapter 36? Do you guys feel that we need to do one more or not, or that's enough? It's up to you guys. I think we did how many so far altogether? From when we started last time to today. Because remember, the more we do, the more you're going to be accountable for your preparation. So I have 1, 2, 3, 4, 5, 6 problems altogether. Okay. Is that enough, or should we do one more? You guys who are here are going to make the decision. The ones who are not here have no votes. Okay. Okay, that's fair enough. So I think 6 is good enough, but hopefully you understand them. Hopefully you guys go through them and make sure that you have a full understanding, because here is the deal. As I was saying, chapter 33 is very light in terms of work. Okay, very good. So chapter 33 is in terms of work is not that bad. It's chapter 34 really that you really need to focus on in terms of image formations and how to find composite image and combine lens with a mirror with another lens or with something else at the end or something else. So that becomes a little bit more involved, okay? Then chapter 35 was really a prelude to chapter 36, because chapter 36 combined the stuff from chapter 35 and 36, because one of them single slit, the other one double slit. But at the end, the problems from this chapter were covering problems from previous chapter. So these 6 problems, including the data problems, including on how to handle Excel and stuff like that is very important that you guys need to master. As I was saying, problems 66 and 67 are for your own entertainment. I'm hoping that you guys go through them and enjoy them. If you have difficulty with them, you let me know, because honestly, I like challenges like this one. So hopefully you're also up to it too. And if you want to work with them, we can work with them, but it's up to you guys. So that's it then. This is the entire course for you guys. As I was saying, thank you for being my students. I'm available for you guys anytime, not necessarily during the period where we're supposed to meet or anything like that. If you have any questions related to the problem, related to concepts, related to things like that, hopefully I can answer them quickly for you, and that removes any kind of confusion or kind of questions. But if you want to, we can go on a one-to-one basis. Now, if I think that one-to-one basis can be beneficial to the entire class, I will ask your permission then to record it for the benefit of everybody else. If the question that, if the discussion basically revolves around your own personal things, basically that you need, then in this case, I will not record those sessions and I will not post them for the other students. It stays private, basically. So that's it. Thank you, guys. It's always sad when it comes to this moment. I'm a very emotional person. I feel kind of, that's the end of it. But we still have exams. We still have stuff that is due, hopefully before the end of the semester in terms of final and another exam. Sounds good? Thank you. Thank you very much. Thank you very much. Okay. So I'm going to stop recording this session, and hopefully the rest of the class can also watch it later on. And the invitation also extends to everybody, not just the people who attend, anybody who is in the class. and has the, very good, thank you. Anybody who has questions is welcome to ask them. So on Wednesday, we really don't, I'm not scheduled anything for you guys, unless you guys have any question, then we're going to meet. Okay, other than that, see you guys next week for the exam, and there is no class on Monday anyway. Thank you guys, bye.